All right, let's look at some topics for the final exam review for the first semester here. Here's some things that you should know how to do. So first, we should find some limits using some graphs. So let's go down here and we'll go a little out of order here. Let's look at f of 0. What is f of 0? Well, f of 0 is 2. Okay, the value of f is the point that's filled in. The limit as x goes to 2, well, as x is going to 2, what is this getting close to? Well, from this side, it's getting close to 2. I'm sorry, it's getting close to a height of 1. So as x goes to 2, the y value has a height of 1, and as this comes from this way, it has a height of 1. So the limit is 1. 3 plus, okay, so this means coming from the positive side or the right side. So as we approach 3 from the right side, the height is 1. And as we approach 3 from the left side, so as we're cruising along our little red graph here, and we're approaching 3 on the graph, what is the height? Well, the height is going to 3. So the y value is 3, going to 3. Okay, and from the left side, it actually is 3. But from the right side, it approaches 1. So remember, we're approaching. This is what we're approaching. From the right side, it's approaching 1. From the left side, it's approaching 3. Well, what is the limit? Well, it's approaching 2 different things, all right? As we come in here, okay, so watch this. We'll do 2 arrows, okay? As we approach from the left and right, they're going to 2 different places here. So this does not exist. They're not going to the same place. Well, let's talk derivatives. Derivatives now is, remember, derivative is the slope of the graph. This is a graph of f of x. So the slope at 1, well, when x is 1, what's the slope of the graph? Or if you want the slope of the tangent line, well, that instantaneous change is 0. So that's a slope of 0. What about at x equals 2? Well, as we come down here, the slope is going down to the right. And from the other side, it's going up to the right. Okay. So these have different slopes on both sides of 2. So, which means it's pointy. All right. So anytime we have a graph that's pointy, we got a little point right here. Okay. Got a point here. Even if it was filled in, okay, it wouldn't exist. This does not exist. All right, f prime of 2.5. Well, at 2.5, that's an x value of 2.5, or right here. So what's the slope right here? Well, it's the slope of that line, which is 2. So the slope is 2. Okay. All right, let's talk limits algebraically here. Well, to find a limit, the simplest way to find a limit is plug the number in. Now, if we plug the number in here, we get 0 on the bottom. 2 squared plus 2 minus 6, that's 0. Plug in 2 here, you're going to get 0. And 0 over 0 doesn't mean anything. So we need to clean this up. So we're going to write this as a different limit. Yes, we need to write that limit out there. Okay, so we have a different limit, and let's factor this. The top factors into, looks like x minus 3. Let's see. 9 times 2, right? 9 times 2 is 18. 2 numbers that multiply to 18 and add to 7. So that would be positive 9 and negative 2. This will multiply out to make that. So that's factored. 2 numbers that add to 1 and multiply to negative 6. I think that's going to be x minus 2 and x plus 3. Well, these cancel, and now we have a limit limit as x goes to 2 of x plus 9 over x plus 3. Remember, our goal is to plug numbers in. So if we plug in 2, well, if we plug in 2, we get 11 over 5, and we're done. Okay? That's it. Well, how about this next one? Now, We got a little typo here. If you look at it as it is, take -4, plug in -4, you get -7. That's not a problem. Plug in -4 here. Now, -4 is a problem because it's a negative number. -4 plus 1 is -3. So that would be a problem because of the square root. Well, anyways, that's not a super interesting problem there. You just can't do anything with it. This was supposed to be a 3. So if yours says -4, let's change that to a 3. Funny looking 3 there, but okay, can we plug in 3? Well, if we plug in 3, we get 0 on the bottom. 3 plus 1 is 4. Square root of 4 is 2 minus 2 is 0. Top becomes 0. So 3 is a problem. So what do we need to do? Well, we need to multiply by the conjugate. So when we have the square roots, the way to get rid of this is multiply by the radical conjugate. X plus 1 plus 2. Put parentheses around this thing. All right. Multiply top and bottom by that. And that's going to give us limit as x goes to 3 because we just changed it. No, you can't change it. I get to change it because I'm the teacher here. So that was the typo I'm going to fix. All right. Now this is an a plus b times a minus b form. A little reminder. A plus b times a minus b is a difference of 2 squares. A squared minus b squared. So what does that mean? That means take this first thing and square it, and we get x plus 1 because the square root goes away, minus, take the second thing and square it, that's 2, and square it, 4. Because notice, -2 times 2 is 4, negative. And on the bottom, well, don't do anything with this. I know it's tempting to multiply it out, but don't do anything. The whole point of doing what we just did is we're hoping that the x minus 3 will go away. And in fact, look at this. What is this worth? It's worth x minus 3. Now I'll go ahead and write this out. You might be able to skip this step and just cancel it, but I'll write it out. The top is x minus 3. Plus 1 minus 4 is minus 3. And the bottom, well, I'm just going to copy that down. Now again, still not multiplying it out because x minus 3 and x minus 3 go away. Don't forget to leave a 1 behind. And now continue to bring this limit along. The limit as x goes to 3 of 1 over the square root of x plus 1 plus 2. Remember, the goal is to plug numbers in. So can we plug it in? Sure. It's not a problem anymore. Plug it in and we get the square root of 3 plus 1. So we have 1 on top and the square root of 3 plus 1. Notice I dropped the limit now because I can actually compute this. I can plug it in. Nothing wrong down here. This is square root of 4, which is 2, plus 2, which is 4. 1 over 4. There it is. Okay. What if we have some compound fractions here? All right. Well, again, plug the number in. We got one more typo. Sorry about that. Okay. If yours has a 3 here like mine does, well, if we plug a 3 in, we get 3 minus 4. That's -1. That's not a problem. 3 plus 2 is 5. That's not a problem. So really, if this was 3, we could plug that in, and that's not a very interesting question. Okay? So the goal, what it was meant to be, was 4. So let's change that. I think these kind of got switched. Well, this is 4, so when you plug in 4, we get 0 on the bottom. Plug in 4, we get 3 over 6. And so we have 1/2 minus 3 over 6, which is 0. So 0 over 0 is what this becomes. Well, we need to clean that up a little bit here. And let's clean up the top. So we'd like a common denominator here. Common denominator is 2 times x plus 2. So we're going to multiply this by 2 on top and bottom. And we're going to multiply this by x plus 2 on top and bottom. See that? Okay. And now we got a common denominator of 2 times x plus 2. Okay. Don't distribute unless you know it's going to do something for you. So I'm not going to distribute that. On top, we get x plus 2 minus 3 times 2 is 6. Okay, and now if we clean that up, let's keep going here. We've got limit as x goes to 4, x minus 4 on the bottom. Look at this, x minus 4 on top, 2 times x plus 2. Okay. Well, what do we do with this? Well, you can think of this a couple ways here. You can think this is over 1. So we want to get rid of that. So let's multiply by the reciprocal. 1 over x minus 4. 1 over x minus 4 on top and bottom. That's going to make this all cancel. And we end up with a limit as x goes to 4. And these 4's are going to, x minus 4's are going to cancel. A little cross-canceling there. It's a useful tool to learn if you haven't learned cross-canceling. That's nice. So the bottom all went away. And we have 1 over 2 times x plus 2 times 1 over 1. So in other words, it's 1 over 2 times x plus 2. Okay? And now, substituting is not a problem. Plug the 4 in. Take that 4. Plug it in for x. 1 over 2 times 4 plus 2. That's 1 over 2 times 6, which is 1/12. All right? So when we have these compound fractions, put them together, clean up the fraction. Hopefully things will cancel, and then plug it in when you can. All right, what about L'Hopital's rule? All right, so L'Hopital's rule here says if it's going to 0 over 0 or infinity, we can take the derivative of the numerator and denominator and then take the limit. Okay, well, is this going to 0 over 0? When x goes to 0, this is going to 0. And this whole thing is going to e to the 0, which is 1, minus 1 minus 0. So plug in 0 for these here, and it's going to be 0. So this goes to 0. So yes, this goes to 0 over 0. So L'Hopital's rule applies. So that means we can take the limit, take the derivative of the top and bottom. What's the derivative of the bottom? Well, that is 1. What's the derivative of the top? Well, the derivative of the top is, derivative of e dx is e to the x. And the derivative of all of this inside is negative 1. So minus negative 1. Okay? And so now we can plug in the 0 here. Plug in 0, e to the 0. We get e to the 0 plus 1 all over 1. And what is e to the 0? Well, it's 1 plus 1. And we don't really care about the 1 on the bottom. It's 2 in the end. Okay? That's L'Hopital's rule. Well, what happens when we're going to infinity? So when we're going to infinity here, we can, the small terms don't matter. So this term will go away because x squared is a lot larger. Now don't erase all these things on the outside, just looking at this small polynomial, that goes away. And these things go away because they're a lot smaller than 9x to the 4th. So just comparing numerators and denominators by themselves. So we can rewrite this as the limit as x goes to negative infinity times, x squared all over the square root of 9x to the 4th. So this fraction is not equal to this fraction. They're very different fractions. But the limit as we approach infinity is the same. So one limit is equal to the other limit. And so this is equal to the limit as x goes to negative infinity of x to the 4th over, now I got to square root both of these. Square root of this is 3. Square root of this is x to the second. When you square roots, this is a 1/2 power. It cuts that exponent in half. Well, we can go a little bit further here. Now, basically, we got a bigger power on top. So once that bigger power on top is there, we know we're going to infinity or negative infinity. I keep putting that fraction bar there. X goes to negative infinity of, well, let's cancel a little bit. These will cancel with a couple of those. And so we have x squared over 3. When you plug in negative a million, negative a billion, negative a trillion, this is going to be a positive number because it's squared. It's always positive. So this is blowing up and becoming a positive infinity. All right. So that's the idea there. Get rid of the small ones as we're going to infinity, small terms, and then clean it up, and hopefully you can figure out what the limit is from there. Great. Well, this next one, there's not a practice problem there. Just kind of said, remember, you should be able to discuss continuity. That means is it continuous? Does it have any breaks? Looking for asymptotes, looking for holes, and things that are domain restrictions. Okay, so if a graph is broken, it's not continuous. If we have some broken graph like this. Okay, now what the intermediate value theorem says is this. If we do have a continuous function, okay, and we know that at A, we have some value f of A, and at B, we have some value f of B. Let's put that over here, f of B. Well, if you pick any number in between there, okay, so there must exist, so if you pick f of C, if we have f of C that's between f of A and f of B, there must be a point on the graph somewhere, okay, where C, some C value in between, is equal to f of C. Okay, in other words, if we say, let's say we have a function here and we know f of 2 equals 3 and f of 10 equals 20. Okay, and f of x is continuous. Got to know that it's continuous. Okay. Is there an x equals c such that, let's say, f of c equals 10? And the big idea, it's not a very fancy question there, so we, yes, since f of x is continuous, and f of c is between 20 and 3, then we can say this: by the intermediate value theorem, there must exist a value of c, so c that's between b and a, such that f of c equals 10. So anyways, that's the idea of the intermediate value theorem there. Okay, just be aware of that. It'll show up in different ways. All right, time for some derivatives here. So finding a tangent line. Tangent line means we need to find the slope and a point on the line. So suppose we have an equation, f of x equals 2x to the third plus 5x. And we want to find the tangent line. You find the equation of the line that's tangent to that. Well, first thing we need is we're going to need a y value. So f of 1 is 2 times 1 cubed plus 5 times 1, which is 7. So that means we've got the point 1 comma 7 that we're going through. And then if we find the derivative here, let's get a different color. F prime of x is, drop the 3. 3 times 2 is 6. So 6x squared plus 5. So plug in 1. So the slope at 1 is 11. So we know that this is going through 1, 7. And we know that it has a slope of 11. So now we can make our equation. Our point slope form, y minus y1 equals m times x minus x1. So we have y minus 11 equals, no, I'm sorry, back it up. Y minus the y value of 7 equals 11 times x minus 1. Okay, so we have our x, y coordinates 1 and 7 and our slope of 11. Okay. Well, our formal definition of our derivative, need to be familiar with that. And that is this. The derivative dy dx is equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. So this is a slope. All right, it's the limit of the slope. Okay, so that's a slope. So let's find the limit. Now, as we see a limit here, if you see an h, you might be suspicious. There's an h in here. It might just be a limit of a derivative here. So, got to ask yourself, is this in this form? Well, be careful. It might not look like it, but I see this cubed, I see this 5, and I see it repeating here. So, this thing right here after the minus is probably the f of x. So I think that f of x here is x cubed plus 5. Let's see if that's true. Well, that would make the rest of this stuff here f of x plus h. Is that f of x plus h? In other words, if we take x plus h and we put it in for x, will this thing here become this? Absolutely. So x plus h cubed, if you put x plus h in here, gives x plus h cubed plus 5. Okay? So yes, indeed, that is f of x plus h minus f of x all over h. So this is in the right form. So what that tells us is that this is the derivative of f of x, which is x cubed plus 5. Well, do you know what the derivative of x cubed plus 5 is? We should. It is 3x squared, and the 5 goes away. Okay? So once you recognize that it's a derivative, don't do all the limit stuff that we did before. Just rewrite it as a derivative and take the derivative. All right. Derivative rules here in properties. So things we've been working with a lot. We got our power rule here. Well, that just means that we can drop this 4 down. 4 times 3 is 12. 3 times 18, 6 is 18. 2 times 34 is 68. And the constant goes away. So there it is. There's y prime. How about the quotient and product rule? Well, here's a product. We need to know the quotient and the product. Okay, so we have the derivative of the first times the second. Well, how do we find the derivative of the first? Well, this also has a chain rule in here. So kind of doubling up on this one here, huh? So we've got a chain rule and a product rule. So chain rule, so kind of stealing from the next one here, says take the derivative of the outside. Well, derivative of e to the u is just e to the u. In other words, it stays the same, e to the x cubed, times the derivative of u. So u in this case is x cubed. So what's the derivative of x cubed? 3x squared. So that is the derivative of the first thing times the second thing plus the first thing times the derivative of sine, which is cosine. Okay, there you have it. And you can leave it like that. If you want to clean it up a little bit, we could factor out this. This is y prime. Don't forget your prime, like I just did. X cubed, we could factor that out, I suppose. And 3x squared sine x plus cosine x. That's a little prettier. But you can leave it unsimplified. All right, the chain rule. All right, chain rule is what we just use when we have something more going on than just a simple x. So here, instead of the secant of x, we have the secant of a big old parentheses of something. So secant, the derivative of secant is secant tangent. So secant of, so y prime is secant of all that stuff times the tangent of all that stuff. So what's all that stuff? In this case, it's x cubed plus 5x squared. X cubed plus 5x squared. And let's clean that up because we ran out of room. Or times the derivative of the inside here. Okay. Derivative of the inside is 3x squared plus 10x. Okay. So there you have it. A little bit going on there, but don't forget the derivative of the inside. Okay. Couple more here, derivatives that is. So logarithms, derivative of a logarithm is u prime over u. So the natural log that is. Natural log of u is u prime over u. So y prime here is the derivative of the inside, 3x squared plus 12x, all over u, which is x cubed plus 6x squared. Well, what if it's not a natural log? What if it's a log base 4? Well, we're going to do just about the same thing. So treat it like a natural log, which is the derivative of the inside, cosine x, over the inside. But then since it wasn't a natural log, we got to multiply by the natural log of 4. We get this conversion factor down there. Okay? All right, there it is. Well, what about our trig functions? So we've used a couple there, sines and cosines. We should be familiar with the derivative of all these trig functions here. Okay, so let's go cotangent here. So the derivative of cotangent is cosecant squared negative. So y prime is cosecant squared, make it negative, of e to the 5x. Now this is a chain rule. That's derivative of the outside. Now we've got to do the derivative of the inside. So what's the derivative of the inside? Well, for e to the 5x, we have e to the 5x times derivative of 5x, which is 5. And we might like this a little cleaned up here. We'd rather write it like this. Negative 5e to the 5x cosecant squared e to the 5x. That would be a preferred way to write it. How about this one? A little implicit differentiation. So when we have x's and y's all mixed up, we got to find the derivative implicitly. That means remembering that y is a function of x here, we'll need to use the chain rule. So let's get to it. Let's take the derivative of this whole thing. So we're taking the derivative with respect to x for this whole thing. So we got the product rule. So here we have 3x times y. Derivative of the first is 3 times the second plus the first. 3x times the derivative of the second. Well, the derivative of y is dy dx. Plus the derivative of 6 sine y. Well, that derivative of sine is cosine. The 6 is going to come along for the right because it's a product. Cosine of y, so that's the outside. Now take the derivative of the inside. Well, the derivative of y is dy dx. And here we go. Now the right side, e to the y. So we take the derivative of the outside, which means just copy it down in this case, because e just becomes its own derivative. That's what's special about it. Times the derivative of the inside. The derivative of the inside, dy dx. Plus cosecant is negative cosecant x cotangent x. Remember, cosecant doesn't go away. It comes right back when you take the derivative. All right, well, we need to take these terms that have a dy dx in them, and we need to get them all on the same side. So let's bring this one over here, and we'll subtract the 3y over. So we'll have a negative 3y minus cosecant x cotangent x. And then we'll subtract this e to the y over. And we'll have 3x dy dx plus 6 cosine y dy dx minus e to the y from the other side dy dx. Then we want to factor out the dy dx. And that leaves us with 3x plus 6 cosine y minus e to the y equals negative 3y minus cosecant x cotangent x. And then last but not least, we're going to divide all of this over to the other side, and that'll solve for dy dx. And it should look something like this. So dy dx equals all this stuff on the right, negative 3y minus cosecant x cotangent x, all over. And we have this stuff 3x plus 6 cosine y minus e to the y. And that's it. So we're going to find the derivative in terms of x's and y's. Okay? All right, and then last little type of derivatives we should review is the arcsines and arccosines and arctangents and cotangents. So the derivative of arctangent is, well, their plain old arctangent is 1 over. So this will be 1 over the square root of 1 minus x to the 5th squared. So 1 minus u squared. But this is going to be negative, first of all, because it's cosine. Cosine goes to negative. And we need to multiply it by u prime, the derivative of the inside, which is 5x to the 4th. So we're going to, okay, so it's u prime over the square root of 1 minus u squared. U is the stuff in the parentheses. And y prime here, inverse tangent. Well, inverse tangent of x is 1 over 1 plus x squared. So this is going to be u prime. Well, what's the derivative of this? Derivative of 5 to the x is 5 to the x times the natural log of 5. There's that conversion factor. All over 1 plus u squared. So 5 to the x squared. And maybe a little cleanup. This is 5 to the x, natural log of 5, all over 1 plus 5 to the 2x. That'd be a little cleaner. Okay, that's the idea. On to curve sketching here. So we got the mean value theorem here. Mean value theorem states that, we want to verify here first of all, so it needs to be continuous and differentiable on this interval. So this is not continuous at x equals negative 4. So this is continuous on 3, 5, continuous and differentiable on 3, 5. Okay, now let's see here. This was going to get a little ugly. But we need to find the average rate of change. Okay, the average rate of change is f of b, in this case f of 5 minus f of 3, all over 5 minus 3. It's going to be 2 on the bottom. When you plug in 5 here, you get 5 plus 4 is 9 squared, which is 81. You get 3 over 81. When you plug in 3, you get 3 over 49. Kind of ugly. Going to our calculator, this is about negative 0.012. All right, we'll go with that. I'm going to use our calculator here. All right. Now we need to find our derivative. The mean value theorem says that there exists a place where the derivative is equal to that. So we want to verify that there. So this is 3 times x plus 4. We need to take the derivative, so let's change that 2 to a negative 2. Let's take the derivative of this. So the derivative of y prime is going to be, the 3 is going to hang out. We're going to drop the negative 2 down, times x plus 4 to the negative 3. Subtract 1 there. And the derivative of the inside is 1, so we would need a times 1, but that doesn't change anything. So this is negative 6 x plus 4 to the negative third. So we want to find out where these are equal to each other. Negative 6x plus 4 to the negative third. All right, which is approximately negative, equal to. We want to find out where that's equal to. Let's just say equals to negative 0.012. So, something like this. We could go to our calculator, but believe it or not, you should be able to solve this. Here's a useful tool. In proportions, we just made a proportion. We can swap this, something you may have done when you were solving with trigonometry. Equals x plus 4 cubed. So if we cube root this, I know this is getting a little long here. Oh well, we're in it now. 6 divided by negative 0.012 equals x plus 4. And I think if we add 4 or subtract 4 to both sides, we'll get a number. And we can go to our calculator and find this out. Okay, negative 4, let's see what that comes out to be. Hopefully it's between 3 and 5. So I plugged in my calculator. I got a wrong answer. Did you see what I missed? I lost this negative, huh? So don't forget that negative. Bring that along for the ride. Negative, negative, which makes this whole thing positive underneath the square root. So changing that there, we get a number of 3.916. Okay, and that is between 3 and 5. All right. Okay, well, that's how the mean value theorem works. Now, does it work here? Is there anywhere that this is undefined? Well, if you remember a square root curve, this square root curve, this is shifted 3, so it's going to look like this. And so is it defined on 2, 3, and 4? No, it's not defined from 2 to 3. So if you plug in 2 on here or 2.1, you're going to have a problem. It's undefined. So it is not continuous, we would say, on 2, 4. If it's not continuous, can't be differentiable. Great. So we need to be familiar with the first derivative test to find critical values and increasing and decreasing extrema using the first derivative equal to 0. And the second derivative finds our points of inflection and concavity. Okay, so here is f prime. So let's find these things out here. So we want to find the extrema. So extrema happen when f prime equals 0. So where is f prime equal to 0? That looks like negative 3, negative 1, 2, and 4. And no parentheses here. Where is it increasing? Well, number line might be kind of helpful here. So let's take our number line. and f prime. So we know that at these points, -3, -1, 2, and 4, that's our 0. So it's negative over here, positive. It's negative because it's underneath. The first derivative's underneath, and positive. So that means we have we're going up. Nope, sorry. We're going down, up, down, down, up. So this is a minimum. This is a maximum. And 2 is neither. And 4 is a minimum. So let's write these as mins and maxes here. So we have minimums at -3 and 4. And we have a max at -1. That's it. So the maximum is at -1. And these are x values, of course. Okay. So increasing is from -3 to -1, and from 4 to infinity. Decreasing from -infinity to -3, and from -1 to 2, and from 2 to 4. Okay. Inflection values, this is when f double prime equals 0. So let's back up here actually. Here f prime increasing, decreasing. So increasing greater than 0, f prime is less than 0. Okay. Inflection values is where it's equal to 0. Okay, so now second derivative is the slope of this graph. Where is the slope of this graph? 0. Well, approximately, let's say -1.8, maybe 1.75, all right? Down here, it looks like it's 0. Down here at 3.5, if you put different decimal, that's fine. Oh, I missed 2, I guess. 2 right there, and 3.5. So it's concave up when f double prime is greater than 0. So that means we have positive slope. I'm looking at the slope here. Where do we have positive slope? Well, we have positive slope from -infinity to -1.75. Then we have negative slope here. So while we're at it, I'm going to come down here. Concave down is negative slope, -1.75 to 0. Then we have a positive slope. Positive slope means the second derivative is positive here. So this is 0 to 2. And then negative slope from 2 to 3.5 there. So we got 2 to 3.5. And lastly, from 3.5 to infinity. All right. Okay, so that's the idea. Okay, so we got this last one, by the way, f double prime is less than 0. Moving on here to an equation here. Okay, so we've got an equation. Should be able to find these things as well from the equation. So if we find the first derivative, f prime of x is, drop the 3 and we get 1x squared plus 4x minus 5, which, by the way, that factors into x plus 5, x minus 1. Okay. And we're going to want to set that equal to 0. And we get extremas at -5 and at 1. And we'll come back and see if their mins or maxes here. So let's go ahead and do a number line here. F prime's at -5 and 1. Let's plug in some values. Plug in -6. We get a negative number. A negative number times a negative number, which is positive. Plug in 0, we get positive times negative. Plug in 2, we get positive and positive. Okay, so we are increasing, decreasing, increasing. Okay, and so negative 5 is a max, and 1 is a minimum. Okay, it's increasing from negative infinity to negative 5, and from 1 to infinity. It's decreasing from negative 5 to 1. What about inflection values? Well, that's second derivative, so let's go second derivative. Second derivative. Don't use the factored version. Use this. Take the derivative. It's a whole lot easier here. Okay, derivative of x squared is 2x. Derivative of 4x is 4. Set that equal to 0. And 2x equals negative 4, so x equals negative 2. So for our second derivative, we have an inflection value or possible inflection value at negative 2. Okay, and we plug in like negative 3. Plug in negative 3 here, and this whole thing is negative. That means it's concave down. Plug in positive or 0 maybe. 0. And this whole thing is going to be positive. That means concave up. The point of inflection value is at x equals negative 2. And we're going concave up from negative 2 to infinity. Concave down from negative infinity to negative 2. All right. So there you have it. There's our curve sketching, all that good stuff. Hopefully you remember that. And last but not least, this has been most recent, so we got optimization and related rates. Here's our application. So let's look at one of each real quickly and call this good here. So optimization, we want to get an equation and take the derivative of it. We can use our calculator. So this is calculator okay on this. Okay, so we want a point on this graph that's near this point. Okay. So we want the nearest, which means closest distance. So we're going to need the distance formula on this. Distance is the square root of x2 minus x1 squared plus y2 minus y1 squared. And in our situation here, we got 1, 4. So let's do 1 minus x squared plus 4 minus y squared. So we've got some point on this graph. Now we know this is our secondary equation, so we know y equals the square root of 2x. So that's going to help us substitute because we need to make this into one independent variable. So to do that, we got 1 minus x squared plus 4 minus the square root of 2x squared. All right. And we want to find the derivative there. We want to set the derivative and make that equal to 0. So here's what I did on my TI Inspire. So we plugged this function into f of x. You can call it d of x if you want, but it gets a little weird with the derivative, so I like to call it f. Be real careful. Just make sure you typed it in right. Looks like 1 minus x squared. 4 minus the square root of 2x squared. Watch those parentheses in the squareds. And then here's a way, I saw somebody do this, so I can't take credit for this idea, but I saw some students doing this where they took the derivative and got this crazy looking thing. You don't need to write this down. And then we want to solve, and what I typed here, actually, I typed solve, and then use the answer key equal to 0, comma, x. And that's a pretty slick way of what it does is it grabs this answer and just throws it in there. So you don't have to do the derivative inside of the solve. That's a little nicer way to do it. So great job, those of you that were figuring that out. So, and then it kind of replaces it for you here. Equals x equals 2. You can do this. Some of us have been doing this. Solve the derivative of parentheses f of x parentheses equals 0, comma x. That will also work. Some of us are getting a little tripped up with these parentheses. So this answer method is pretty slick, so you don't run into parenthesis problems. Okay? So either way it works. We got x equals 2 there. Okay? So when x equals 2, and if we plug y in there, y equals the square root of 2 times 2, which is the square root of 4, which is 2. So that gives us the point 2, 2. Good for ballet, too. All right, cool. Well, one last one, related rates here. Okay, so let's see the situation. We have a circle with a radius of r. Good idea to draw pictures here. We got a circle with a radius of r, an area A and a circumference C. R is varying in time t. And so the question is, for what value of r is the rate of change of A with respect to t twice the rate of change of C with respect to t? Well, lots going on here. So we're talking about area. Good idea to write an equation down. Okay, when you're just gathering information, just we need to start to get equations together, whether they're useful or not. Let's get them down. Circumference. Hopefully you know that circumference is 2 pi r, also known as pi times diameter. 2 times the radius times pi. Now, it's talking here about r varying in time. It's talking about a with respect to t, the change in a with respect to t. Well, how do we get that from all this? Well, we need to take the derivative with respect to t. We need to find the rate of change. And we do that implicitly. So that's dA dt. Now we take the derivative of the outside here. That's 2 pi r. That's the derivative with respect to r times dr dt. dr dt is the inside. That's the implicit part. What about the derivative of c here? Well, that's dc dt equals 2 pi times dr dt. We got an exponent of 1 here, so drop that 1 down. The r goes away because we subtract the 1, but you got the inside dr dt. So now we got our dA dt's and dc dt's. Now this one has a little unique twist. A lot of these problems have a little unique twist, and that's okay. Just start writing it out. We were not told the radius or the change in the radius, okay, which of course we're trying to solve for radius. What value of r? That's what we're looking for. But we got this little situation here where the rate of change of A is twice the rate of change of C with respect to t. So let's write that as an equation. So we know dA dt is twice, so 2 times dc dt. Well, we know what dA dt is. There it is. So we can drop that in there. We know what dc dt is. We can drop that in there. Let's see what we get. Now again, if you're not sure where to go, just start making substitutions. Be careful. Use your algebra properly. Okay, this is proper algebra. We're allowed to do this because this is what dc dt is worth. We could clean this up a little bit. 2 pi r dr dt equals 4 pi dr dt. Now here's what we need to understand. We need to understand that dr dt is just a number. That's a variable. It's not, and it looks complicated. It's got 4 letters there, but it's just a variable, okay? So that's worth some number. What is it? I don't know, okay? So, but we can divide both sides by dr dt. And those just go away. So in other words, 2 pi r equals 4 pi. And remember the question was asking us, what is r? Well, we can solve this for r, right? Divide by 2 pi. R is 2. What are our units? Does it say? No, it doesn't actually say, right? I don't think there's any units there. But it doesn't matter because look at it, it's a multiple choice here. So 2 is the answer. All right. Well, I hope that helps. There's a good overview of everything we learned this semester. Okay, so for the final there, we just got a little smattering of everything there, right? And not getting too deep, but hopefully understanding the big ideas. Keep in mind big ideas. Big ideas, things like derivatives equal to 0 at the extrema. Second derivative equals 0, point of inflection, okay? These are the big ideas. So always start by looking at big ideas and then work from there.